This is the lecture video for Algebra 2, Chapter 2, Section 1, which covers functions and relations. So everything we're going to be looking at is going to be defining the difference between a relation and a function, and basically we're going to be looking at the different ways of representing ordered pairs. So we're going to be looking at graphical approach, mapping, actual ordered pairs, and then making an XY table. So these are things that we're going to be using for the next for this chapter and for every graphing section that we have from here on out. So if you have questions, make sure that you get them asked and answered as soon as possible. So here's your video.
Alright, so this is the lecture video for Chapter 2, Section 1, which is over relations and functions. So first of all, we have a relation and we have a function. So a relation, it's kind of like when it comes to your family, right? A relation is somebody that's close to you, okay? They're part of your family, but it can be extended or immediate. So a relation for us is a pairing of input and outputs. So that's our connection, right? Things are related because they're part of a pairing of inputs and outputs. Now the domain is simply a set of all input values, but when we write it, the domain is always going to be in curly brackets, and it's going to be listed from smallest to biggest, which is the ascending order, and we're going to have no repeats. Okay, the range then is the set of all output values, and it's going to be set up the same way, in curly brackets, no repeats, and ascending order. Now, a function is a special kind of relation. It is a relation that is considered one-to-one. Now, for us, one-to-one, we're relating things, right? For every one of this, we have one of something else. And that what we relate is the inputs and outputs, okay? So when we say one-to-one for a function, what we're actually talking about is for one input, we have exactly one output, okay? So relations are any kind of a pairing, and functions are special relations. So let's take a look. Here we have our relations, our ordered pairs right here. Now, first of all, they're called ordered pairs because they're pairs, which means that there's two of them, so two values, and they're in order. Now, in order for us is going to be alphabetical order, so X, Y. And that's how every point's going to come to you, is the X is going to be first, and then the Y. Now, for us, for the mapping diagram here, this is called the input table, and this is then the outputs, okay? But there's other names too. Which variable for us is the input? Well, which one do you always get to pick on your own? That's the X. And because we get to pick it, it's also the independent variable. So when they say independent variable or the inputs, they're actually just talking about X, okay? Similarly, we have the outputs over here, but we also have the Y's, and this is also the dependent variable. Okay? Now, we don't really use input-output too much, or independent-dependent, but what we do use is we use domain and range. So remember, the domain is the list of all inputs, and so the domain is the list of all inputs, and the range is the list of all outputs. Okay? And what we're mapping here is we're mapping the two variables. So if you notice, I have an X of -2 here, and it relates or maps to a Y of 2. So I start at -2, and I need to draw an arrow to +2, which is right here. Okay, -2 to -2, same thing. An X of a -2 maps to a Y of a -2. 0 maps to 1, and 3 maps to 1. Now, in order for something to be a function, it has to be 1-to-1. And what that means is for every input, we get exactly one output. Now, if you look, do we have any inputs that have multiple outputs? Yeah, -2 right here, correct? -2 maps to -2, and -2 maps to 2. So why do we use the mapping diagram? Because it's really easy to determine if something is a function or not. Just look right here. How many arrows are leaving the input of a -2? Right, we have 2 arrows, but we need things to be 1-to-1, which means only 1 arrow is leaving each of the inputs. So if I ask you, is this a function? You would say, no, this relation is not a function because it is not one-to-one. Okay? So that's what you're going to say. So you're going to answer the question with a yes or no, but then you have to justify it. You have to back it up, okay? And when you justify something, you have to use the definition. So we're saying that this is not a function here because it does not satisfy the one-to-one relationship that we have to have in a function. And you can word that pretty much however you want. Okay, so here are some other representations of the exact same ordered pairs. So first of all, we have the relation listed as ordered pairs right here. So these are all xy's, xy, 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 xy. Here's a graph. So first of all, which axis is the x-axis? Right, that's the horizontal, which makes the vertical the y. And then for our first point there, negative 2, 2. Right, when you graph, you always start at the origin, which is 0, 0. The first number is an x, so that's either going to move us to the left or to the right. And then the second number is a y, which means that it's going to move us up or it's going to move us down. So for our first ordered pair, we're going to start at 0, 0, and we're going to move 2 units to the left because this is a negative direction, right? This is negative 1, negative 2, positive 1, positive 2, positive 1, positive 2, negative 1, negative 2. So up is positive, down is negative, right is positive, left is negative. So we're going to go to negative 2, 1, 2. So that's the first value from right here. Now our y says we go 2, and it's positive. So from here we go up 2, 1, 2. And as you can see, that's where your first point is. Our second point is negative 2, negative 2. So we go back to the origin, go 2 units to the left because our first number is a negative. And then our second number is a negative, so we're going to go down 2 from there. And you're going to repeat this process for every point. So 0, 1, you start at the origin. 0 means that you do not move at all left to right. And you're going to move up 1, and there's your point. And then go back to your origin, and your last point is 3, 1. Okay? Now, here we have 2 tables. You can make your XY chart horizontally, like we did right here, or you can make it vertically. It does not matter as long as your X's and Y's are clearly labeled and things match. So you notice our first point here is negative 2, 2, with X being a negative 2 and Y being a positive 2. If you look at the vertical representation, it's the exact same thing. X is negative 2, Y is 2. Again, style is up to you. Do what you're comfortable with and what you know you can do properly. Okay, the vertical line test. This is a graphical approach to determine if something is a function. What the vertical line test says is that as you grab a vertical line and you trace your graph, okay, so we're going to trace this graph, is there ever a point where the vertical line is going to intersect with our graph more than one time? All right, so that's what we're trying to look at. So as we grab our vertical line and slide it here, you notice that it's intersecting just one time right here, and as I slide it, we always intersect this graph exactly once. So what that means is that the function, so what that means is that the relation is one-to-one. So if I asked you, is this graph a graph of a function, you would say yes, the relation is a function. But remember, we need to always justify what we're saying. So because it passes the vertical line test. The vertical line test. So again, if I grab a vertical line and I drag it over my graph, do I ever intersect more than one time? No, I do not. Therefore, this is a function. Let's do the same thing over here. Okay? Does this graph ever intersect the vertical line more than once? Yeah, it'll intersect once here, and it will intersect once here. So as soon as you get one time or one position where the vertical line intersects the graph more than once, you're done, and you can say no, the relation is not a function. because, again, we have to justify, because it does not pass or fails the vertical line test. Okay, so that's what we're going to be looking at here for the vertical line test, is you're going to have a graph, and you need to have some kind of a vertical line, so a lot of people use their pencil and just trace the graph. Okay, here we intersect more than one time, therefore this is not a function. Over here, everywhere I can drag this vertical line, we're only crisscrossing or intersecting the graph one time. That means that what I have is, in fact, the graph of a function. Okay, an equation in two variables. We've already talked about this. The independent variable is the one that you get to pick, so it can change. Okay, it can be whatever you want it to be. So this is going to be, for us, the x variable, because this is the one that we pick. So it's the picked variable, or the picked value. Okay, now the dependent variable is going to be, for us, it's going to be the y variable, and this is the one that you find. So this is the one that you solve for. So this is the value you find. Okay, and the independent is always your input. So if you notice, the ins match, and then that means that the dependent is your output. Okay, so if they ever ask you what's the independent variable for this situation, all you have to ask yourself is, which one am I plugging in for? Which one am I putting in as the input? That value, or that variable, is your independent variable. The dependent variable is the one that's by itself. It's isolated. It's what you get out. Okay? So as we work through these, that terminology will be a little bit more useful to you. Okay, so what is a linear equation? Many of you, I hope, remember this. All right, so what is a linear equation? We've already talked about it, but if I gave you an equation like that, is this a linear equation, yes or no? So first of all, if I asked you which variable is the independent variable, that would be the x, because it's the one that we plug into. Okay, that's the input variable. And the y, which is the variable that's isolated, that's going to be our output variable. So that is the dependent variable. So it's kind of weird that the variable that's independent is the one that's not by itself, and the variable that's dependent is the one that's actually isolated. So, linear equation. Does anybody remember what a linear equation looks like? Okay, then I'll go back through it. So, a linear equation is an equation whose highest power on x is 1. So, if we look at x, what is the variable? So, if we look at x, what is the power on x? Right, we only have one x, and if you look right here, the power is not written, which means that it has a power of 1. That is a linear equation. So yes, this is linear. Okay, and the only reason why I know that is because the biggest power on x is 1. So what if I were to write something like this? Is that a linear equation? No, because what's the biggest power on x? Right, it's a 2, so not linear. Okay, the only reason why we're really going to be using this is to try to determine what a graph should look like before we actually get to the graphing stage. So it's just to help us foreshadow what's going to actually happen throughout our process. Okay? So, graphing a linear equation. Now, there's a couple of different ways of graphing, and I'm going to show you both methods right here. Okay, the first thing is, if you notice, is y by itself in this equation? Yeah, it is. So that means that I can use my y equals mx plus b. So remember, this is standard form for an equation where m represents the slope and b is your y-intercept. So first of all, what's my m? Well, m is always the coefficient on x. So what's the number in front of x? Right, it's going to be a 1. And we always want to write slope as a fraction, and I'll show you why in a second. Okay, so now what's our b? Right, that's 2. Okay, So these are the only two things that you need in order to graph an equation. So the first thing is we need to know where to start. We're going to start with B. And like I said, this is a y-intercept, which means that it's where we're going to crisscross or intersect the y-axis. So first of all, was the y-axis the horizontal or the vertical? Right, it's the vertical it's the vertical axis. So we're going to go to 2 on the vertical axis. 1, 2. This is our starting point. From that point, we are going to use our slope. So our slope is 1 over 1. So is this numerator a positive or a negative? Right, it's a positive. And why that's important is because our slope is always rise over run, which means this is y change over x change. So what it tells us is that if we know one point on our graph, we can use the slope to find all the other points. So this is a positive, so that means that we're going to go in the positive y direction. So from our intercept, we're going to go up 1. Okay, the denominator is 1, but it is also positive. So remember, the bottom is the x move. So from here, we're going to move 1 unit positive, though, which is to the right. And that's what the slope says, so there's our second point. Now, remember, it only takes 2 points to make a graph. So now that we have our 2 points, we're going to go like this. We're going to make our graph and throw our arrowheads on because our line goes forever. And that's it. You're done. Now, if you don't see that, or if you're not comfortable with it, then you can actually make a table. So what we're going to do is we take this x value and plug it into the equation in order to figure out what the y is that goes with it. So everywhere we see x, we replace with the x value that we wrote outside. So what is negative 2 plus 2? Right, that's 0. Okay, plug in a negative 1 plus 2, and that's going to give you a positive 1. Plug in a 0, and we're going to get 2. Plug in a 1, we're going to get 3. Whoops. All right, plug in a 1, and we're going to get 3. Plug in a 2, and we get 4. Now, if we plot this, if I did my line properly, I should be really close to what I already have. So at negative 2, 1, 2, I should be at 0, which is right here, which is just off my line. At negative 1, I should be at 1, which is on my line. At 0, I should be at 2, which is on my line. At 1, I'll be at 3. And at 2, I'll be at 4. So as you can tell, every point that I found from the table over here is exactly the same points that I have on my graph over here where I use the y equals mx plus b format. So it does not matter which method you use. What matters is that you can accurately graph on a Cartesian coordinate plane, either using y equals mx plus b, which we call slope-intercept form, or by using an xy chart. Okay, so remember, if they ever ask you to graph on anything, whether it's the ACT or it's a science class, if they ask you to graph and they give you the function and you don't know how to graph it, just make an XY chart and run these 5 values, negative 2, negative 1, 0, 1, 2, and you should get a really good picture, at least a basic idea as to what the picture should look like, and you can figure out what is accurate and what is not accurate based off of those values. So I know a lot of students get really frustrated with graphing. Just do what you can, but make sure that you're sticking to your 5 values and you're looking at whether the function's linear or not to help you determine what the shape should be before you even start graphing. Okay? That's the fastest way to do this stuff on the ACT, is just look at whether the graph is odd or even. Is it linear? Is it a quadratic? And then you can usually throw out 1 or 2 right off based off of that. And then take your 5 values and check to see which ones exist on the appropriate graph. So that's kind of a shortcut on where, before you even start graphing, you should have a basic idea as to what the graph will look like in the end. All right, so here's your homework assignment. Good luck if you get stuck. Make sure you watch the homework video. And as always, these problems are complements of the Algebra 2 Michigan edition distributed by McDougal Littell.